Hello, and welcome to today's session on speech perception. Speech perception is pervasive in our everyday lives, and today, during our discussion, we're going to try to understand the nuts and bolts of how speech perception works so effortlessly. Okay, so we'll begin with a question that I'd like you to muse about before coming to class, and we'll begin our class session on this particular question. The question is, what distinguishes human language from the way other animals communicate? We know that human language is really very different in many ways from the other kinds of animal communication that we see across the animal kingdom. So the question again is, what distinguishes human language from the way other animals communicate? I'll be interested in hearing your speculations on that. Okay, we're going to jump right in and talk a little bit about the phoneme, a very basic unit of speech, and let's see if we can first define it. A fundamental unit of speech is the phoneme, a sound difference that affects the meaning of an utterance. Okay, and we'll see if we can give you an example or two. Consider the N in the word pronounced win versus the word pronounced win. Okay? So in one case I'm saying win as I normally would. In the second case, win, I'm hanging on to that N. Although you can hear the difference, the extended N sound does not change the meaning. So the extended N sound is not a phonemic difference. So the difference between win and win is very clearly discriminable, but the meaning of the word hasn't changed. And because the meaning of the word has not changed, then we would not call this particular difference a phonemic difference. Okay, now let's contrast all of that with the difference between win and wind. There is a phonemic difference there, since the meaning of those two utterances is different. So win, wind, those two utterances mean different things. And what I find particularly interesting about that, and I hope you do too, is that it might even be the case that in everyday language, win and wind are not phonetically so distinct from each other, but you can barely make that distinction, and there's an important meaning difference. If I say win and win, there's a very clear discriminable difference, but that difference that's easily heard is not one that has a meaning. So not all phonemic differences are really easy to hear, but whenever there's a phonemic difference, we have a change in meaning. Native English speakers typically produce about 12 phonemes per second. There's a lot of variability in that. I'm a relatively fast speaker myself. I probably produce more than 12 phonemes per second in most cases. And there's regional variability, as we'll come back to later on in the phonemic production. Interestingly, people can typically comprehend up to 50 phonemes per second. So we can talk about speech production, and we can talk about speech reception, and our receptive capacities typically, in most cases, will exceed our productive capacities. This is a very common phenomena in language. Okay, unlike pure tones, a phoneme comprises many frequencies. So let's just remind ourselves what pure tones are. When we talked in earlier sections about the Fourier analysis, we mentioned that we can decompose any complex sound into these sinusoidal components that we call pure tones. Okay? So pure tones might be sinusoidally modulating, but that's not true for the phonemes. The phonemes have many different frequencies in them. It's a rich combination of many frequencies. Phonemes and all other sounds can be characterized by what we call a spectrogram, a plot showing how much acoustic energy is present at each frequency across time. So what's interesting about that is we have three variables right there in the spectrogram. We have frequency, we have the amount of acoustic energy, and we have time. All of those are going to be represented even on a two-dimensional graph. So this is always a challenge. How do we represent three variables on a two-dimensional graph? Let's take a look at a spectrogram and see how that might come about, these three variables. And we'll take very simply the word spike, just as one example. So here's the word spike being uttered across time. So time was one of our three variables, and we have that on the x-axis. In a spectrogram, by convention, we typically have frequency plotted from low to high. That's expressed in hertz, or cycles per second. So in this particular case, we're going from 0 to 4,000 hertz. And normally what we would need is to represent on the spectrogram the third variable, which would be the amount of acoustic energy. We can think of that as being the amplitude in our FAPO designation, our FAPO acronym. And that's usually reflected here by varying shades of gray. in the video that we're watching right now, it might be that these all of the shading looks black to you. But you can imagine that we can have various shades of gray, where perhaps the darker shades of gray convey higher levels of acoustic energy, and the lighter shades of gray might convey lower levels of acoustic energy. In colored spectrograms, you might have something like the red areas corresponding to high levels of acoustic energy, or whatever energy you're measuring. Blue might correspond to lower levels, and we might take advantage of the Roy G. Biv spectrum to color our spectrograms. The same red-blue convention is used in MRIs and PET scans. Many of you see these in everyday news blurbs on the internet. You can see these spectacularly colored pictures of the brain that come from MRI or from DTI, diffusion tensor imaging. And we use different colors to reflect, in that case, maybe different levels of activity. Here we can use different colors or different shadings to reflect different levels of acoustic energy. Okay. Let's take a look at this, and we might ask ourselves, in this particular spectrogram, which again shows our three variables, we have frequency, time, and the darkness in this particular case reflects the amplitude of energy. Which word is most emphasized here? Okay. The utterance is, "Where were you last summer?" It's a 5-word utterance. Okay. Note, in everyday life, shifts in acoustic energy affect the connotation of a sentence. Okay, so we'll have you think for a moment about which of these might be most likely to be emphasized. And to pick up on this point about the changes in connotation, I'm going to give you a different 5-word utterance. And I'm going to say the same 5-word utterance many different times. And across the variations, you'll hear that sometimes I'm emphasizing different words. And you might think about, how would the spectrogram change as I make these different utterances, always consisting of the same 5 words. So here come the 5 words. And they are, Joe bought flowers for Mary. In that first utterance, I tried to say that as flatly emotionally as possible. Joe bought flowers for Mary. Now what I'm going to do is play around with the connotation very subjectively, and I'll ask you to think about how the spectrogram might change for each of these pronunciations. So here comes the first variation. Joe bought flowers for Mary. Here's the second variation. Joe bought flowers for Mary. Here's a third variation. Joe bought flowers for Mary. And finally we have Joe bought flowers for Mary. Okay, you might ask, how does the connotation change in each of those? And then correspondingly, how might we map those changes on a spectrogram? What kinds of features within the spectrogram would be changing across those different connotations? It's also interesting to remind ourselves at this point that so much of what we do in college and in our everyday lives would entail reading. And when we're reading something, we lose a lot of the richness that can be conveyed not only with the facial expressions that you're seeing as I'm making those different utterances, but we also lose the richness that would occur in the spectrogram. That we get different kinds of connotations. We get the sense that an interrogative or a question is being asked, maybe when we get a frequency sweep upward or downward. So it's very interesting to think about how flat our emails are and how flat and one-dimensional our texting might be. And the spoken language can be very rich, and some of that gets revealed in the spectrogram. Okay. There's a correspondence between the ordinate of the spectrogram, which indicates frequency from low to high, and the activity of the basilar membrane, which performs a frequency analysis on incoming sounds. Let's pause here before we go to our next slide and ask us to think of the gesticulation that we make to show the transductory process for hearing. We talked about how we have a transductory process of a cis-trans isomerization in vision. We learned a gesticulation a few sessions ago for how we signify the transduction process for hearing. And we'll see if you can recall what that is. Give you a moment to think about that, and we'll give you a moment to actually do that gesticulation. Okay, so for those of you who are recalling, we have the basilar membrane represented this way, and here we have the organ of Corti. The lower portion of the organ of Corti is the tectorial membrane. We have now the basilar membrane on the bottom, and these two will begin sliding back and forth over each other. And when that happens, we're going to get the release of neurotransmitters from the cilia, or the hair-like particles on top of the inner hair cells and outer hair cells, all driven by this motion, this back and forth motion. The back and forth motion arises because there's a wave, a traveling disturbance, in the fluid-filled cavity that is the middle ear. And of course, that traveling disturbance arises from the stapes, which is one of our ossicles banging on the oval window. Okay? So that's just our little recollection about the basilar membrane. And now let's think about it this way. Here's another spectrogram. Here we're saying the word spike one more time. Okay? And we might ask you this question. Which end of the ordinate, that's this y-axis, which is showing frequency, which end of the ordinate is apical and which is base on our basilar membrane? Here, the word base is spelled B-A-S-E, okay, not B-A-S-S. So which end of the ordinate is apical and which end is base? We'll let you think about that for a moment, and I look forward to your response to that in class. Okay, let's see if we can go on. Although the spectral content, and what we mean by spectral content is the amplitude at each frequency range, although the spectral content provides cues about speech sounds, a difference in spectral content does not necessarily generate a difference in perceived speech sound. Okay? So there's a lot there, and we'll unpack that. But before we do, I do want to take one, I think, important side note, or make one important side note about spectral content. Some of you who have taken chemistry courses might be familiar with spectroscopy. This notion that we can analyze different chemicals by looking at the amount of electromagnetic radiation that we have in different frequencies. So we can even have, for example, a spaceship flying by the surface of Mars or one of the rings of Saturn, and we can project from that spaceship down some electromagnetic energy and see what gets reflected. And some wavelengths of light, some frequencies, are going to be reflected much more saliently than others. Other wavelengths and frequencies are going to be absorbed. And by looking at the distribution of reflectances and seeing how much amplitude we have in each frequency range, we can glean some information about the content chemically of a surface, maybe the surface of a different planet. We can use exactly the same principle to glean information about speech. We're looking at the spectral content of speech stimuli, and we're coming back to this idea then that although spectral content provides cues about speech sounds, a difference in spectral content does not necessarily generate a difference in the perceived speech sound. This is the notion of a many-to-one mapping. That is, a given speech sound can have more than one image in spectrograms. To make an analogy to yet a different science, many of us are familiar with this distinction between a phenotype in biology and a genotype in biology. And one of the interesting things that we learn about the relationship between phenotypes and genotypes is we can sometimes have a many-to-one mapping. That is, we can have different kinds of genotypes arise or give rise to a given outcome, a given phenotype. And that's what we have going on here in speech perception. A given speech sound can have more than one image in spectrograms, a many-to-one mapping. Okay, so let's take a specific example. The spectrogram reveals that the D sound, okay, that's the fourth letter of the English alphabet, the D sound rises in the syllable di, but falls in the syllable do. Okay, and let's see if we can get a picture on that. So let's orient ourselves. Here we're going to have the passage of time for different utterances, both beginning with D, the fourth letter of the English alphabet. Here we have the utterance di, and here we have the utterance do. And we can see how we get a spectrogram for each of those syllables. Here we have the frequency range. Okay? The D can rise or fall depending on the vowel sound. Okay? So when I say di and when I say do, okay, you hear a D sound in each of those cases. But if you look at what's happening in the spectrogram, we can see these little rising and falling portions that we refer to as formant transitions. Okay? So these rises and dips are called formant transitions. Okay? And they happen over very brief units of time, maybe on the order of a few milliseconds, maybe tens of milliseconds. We have these little bits, and both of those are going to map to our perceptual experience of the D sound, even though they're very physically different from each other. Okay? So you might say that in a sense, this would be an instance of a metamer. You might also say that this is a many-to-one mapping. Different kinds of genotypes, if you will, are mapping onto this perceptual phenotype that we call the letter D. Okay? Formant transitions are cues to consonants. So here, even though this one is different from that one, we are getting a particular kind of pattern that you and I might recognize as a D sound. And once again, there might be many different patterns that map onto the D sound. But there would be an ensemble of yet other patterns that might map onto a different consonant sound, like, for example, the W sound or the M sound, and so forth. Okay, let's see if we can understand a little bit more about what's happening on the spectrogram, we have these formants, okay, inside of our spectrogram. The vowel-related horizontal bands, shown here, 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 and here, are called formants. And formants are amplitude peaks in the frequency spectrum. So if we were to look at the frequency spectrum, we'd see that we have a lot of energy here and here as we say di, and we have a lot of energy here and here as we say do. Okay? And even though they both sound like they're starting with D, we get these, in fact, they very compellingly sound like they're D sounds. We get these different formant transitions, and we also have different formants helping us to understand what it is that's going on in the di sound versus the do sound. Okay, so let's see how the formants make vowel sounds distinct from each other. We'll see spectrograms in which consonants, the formant transitions, have been eliminated just for simplicity. And I think you'll find this to be really, really intriguing. First, let me apologize for having lost in this particular diagram the y-axis label. As always, that's going to be frequency. It's going to go from low to high, and this is expressed in hertz or cycles per second, as always. We have on the x-axis something that's a little bit different than what we typically see. We saw something like this in the preceding slide. These values are actually categorical values. Most frequently in this course, we have a continuous variable, maybe like time or space or frequency plotted on this axis. Here we have just individual word sounds. And specifically, we're going to be emphasizing here vowel sounds. So here, for example, is B. I'll go to the other extreme. We have oo as in tooth. And then on this plot, we're showing you the formants that would be uttered by the typical adult male. So these are men on average. And over here, we have the same vowel sounds being uttered by children versus men. And we'll see how are these similar and how are they different. Very interestingly. Let's start out with the long E sound, as in the word be. Okay? And what you can see is we're showing that we have three formants, three amplitude peaks in the frequency domain, and we're getting one that's relatively low in frequency, and then there's a very big step in the frequency domain before we get to our second formant, and then our third formant is just a small step away from the second. Okay? So we have big step, small step. Let's take another example. We'll go all the way over here to the oo sound. That's two O's, as in the word tooth. Okay? And we have, again, three formants, three amplitude peaks in the frequency domain. And the first one is lining up at about the same level as it is for the word be. So those two are not distinguishing one vowel sound from the next. But if you look at the step size here, we go up only a relatively small step in the frequency domain before we come to our second formant, and then we have a comparatively large step size between the second and third formants. So the overall pattern here might be something like big step, small step for the E sound, and then small step, big step, if you will, for the oo sound. Okay? So that all by itself might be a cue to the listener that we have different sounds out there in the distal stimulus. Now let's take a look at how that might change and how that might remain the same if we go over here and do the same analysis for children speakers. Here we can first observe how children tend to differ from men. Unsurprisingly, we would expect that children would have higher pitched voices, and we see much more acoustic energy in these upper frequencies for children than we do for the corresponding formants here for men. So we get what we would expect, higher pitches for children, higher frequencies for children than we do for men. What's interesting, though, is even though the stimulus has changed and slid upward in frequency, we still get, generally speaking, the same pattern of formant distributions. Let's go to the E and the oo sound one more time. And just like we had before for the adult males speaking E as in B, we get a big step, small step. We get that same kind of big step, small step pattern here in the children. Let's go to the other one. We said that for oo, as in tooth, we had small step, big step. For children, again, we have small step, big step. So even though there's been a shift in the overall level of frequencies, children having higher frequencies than men, the patterns, the relative distributions of these formants remains somewhat constant. And Gibson would tell us that this is an invariant. The Gibsonian invariant is a very important concept in how it is that we can perceive constancies, something like the E sound or the oo sound, across very different speakers who have very different frequency ranges. We can pull out some kind of pattern analysis in what he would call an invariant. Okay? So the invariant here would be big step, small step, I get that over here, big step, small step. The fact that it slid upward in general for children is irrelevant. Here we have small step, big step, small step, big step, same pattern even if they're not happening in exactly the same ranges. So very interesting how we're able to use formants to help us distinguish vowels. Something else that you might know about vowel sounds is that regional accents are determined by differences in vowel sounds. Earlier I mentioned that people from the Northeast might have a relatively fast rate of speech, but we also have regional accents that have nothing to do with the rate of speech. Sometimes it's just the vowel sounds that are distinct one from the next. And one, I think, very salient example of this was given to me when I was a postdoc at Columbia University. I had the good opportunity to be the organizer for the Columbia University Neuroscience Journal Club in one of the years that I was a postdoc, and we had a member of the psychology department who specialized in linguistics come to join our neuroscience conversation. This was Dr. Larry Huer, and he made a very interesting claim. He claimed that Californians have a reduced phonetic space, and this was the example that he gave. He distinguished between the words C-A-U-G-H-T and C-O-T. So many of us might pronounce this cot, and some of us say caught. You can almost hear this long W sound. He was making the point that in California, many speakers use this pronunciation cot for both of these words, cot and cot. Okay? So we would say, for example, a person slept on a cot, and a baseball player caught the ball. Okay? There is a distinction to be made there, but not all speakers in all regions will make those distinctions. Here's another example. My father's name is Don, D-O-N. One of my graduate school buddies, her name was Dawn, D-A-W-N. So I say Don and Dawn. I had a friend, a different grad school buddy, who grew up in New England, and he also said Don and Dawn and made a phonetic distinction, but he reversed those relative to the way that I did. For example, D-A-W-N is pronounced Don, and D-O-N is pronounced Dawn. So here we have an example where somebody is making the phonetic distinction, but people from different regions, I'm from New Jersey, he was from New England, we have inverted how we assign these letters to those different phonetic sounds. So lots of regional variations in vowels, and we can track all of that by looking at the formants. Okay. We hear different consonant sounds because we are sensitive to various aspects of formant transitions. For example, for a given vowel sound, the neighboring consonant sounds could be distinguished by the duration of the formant transitions. So let's have a picture, say 1,000 words for us, and we'll take a look at one more spectrogram. Here we have frequency as always, and for any one of these categorical pronunciations, get, yet, and viet, we have the time domain shown here. So here we have get, and you might notice that we have a very sharp, very steep slope. So we're getting something of a frequency sweep. If I could play this for you, it would sound like hope those whistles came across adequately on the video. The point is that we have very brief durations in which to make consonant distinctions. Here's the G sound, here's the Y sound, here's the V sound, always with the same endings. The ending is going to be et in each of these cases, and you can see that we might have something like 100 milliseconds in this span on the x-axis. So this transition, this formant transition, is happening over an interval of time that's briefer than 100 milliseconds. This one might be taking about 100 milliseconds, and this one's taking substantially longer than 100 milliseconds. Okay? Okay, so consonants can be distinguished by the duration of their formant transition. That's one of the cues, anyway, that helps us to understand these, which consonant is which. So detecting subtle difference in the temporal structure, that's the time-based structure of acoustic energy, is critical for speech perception. And we do this all the time. Some people lack this ability, and it creates a learning impairment. Maybe stated more appropriately, we differ from each other in the sensitivity that we have in these fine temporal structure manipulations or variations in the frequency domain. Some of us can pick up very, very small changes in time and frequency. Others will need a longer duration of time to experience that change in frequency. So there's a lot of variation, and if you're at the low end of that distribution, then you might be classified as having some kind of language impairment. And the one that we're going to focus on is something called a language-based learning impairment, sometimes abbreviated LLI. a limitation in language skills that arises from the inability to discriminate transient acoustic features associated with speech sounds. So LLI affects about 5% of children, most of whom have perfectly normal audibility functions. So let's just see if we can understand very precisely what we're talking about when we're referring to LLI. You can imagine that a teacher is in front of the classroom and she or he is producing phonemes at something like 12 phonemes per second, and maybe more than 12 phonemes per second. Okay? For most kids, under most circumstances, that's going to be just fine. But if you can imagine having a language-based learning impairment, you would need wider intervals of time in order to understand what phonemes had been uttered. And if the teacher's speaking relatively quickly, if she also or he also happens to be speaking relatively softly, then we have low levels of acoustic energy that are whizzing by at very fast rates, and some children are going to be missing that, and they're going to be missing a lot of information about what the teacher is saying. Okay? So these children can hear, but cannot understand speech as well as other children. I mentioned a moment ago that when you test these kids, they have normal audibility functions. I'm going to show you now what an audibility function looks like. Okay. Here's a typical human audibility function, just so you can see the axes very clearly. In this case, frequency is now on the x-axis. And over here, we have the sound intensity that's needed for you to correctly identify which of the two ears the sound might be played in. So many of you might have done this in elementary school. You might have gone to the school nurse, or maybe the school speech pathologist, or whatever the school assistant might have been, and they have you wear some headphones or earbuds, and they play for you different sounds, and your job is to raise your right hand or your left hand to indicate which ear had been stimulated. And while you're playing this game, the audiologist is manipulating the different frequencies, they're adding various levels of intensity, and they can create one of these audibility functions, which is a little bit conceptually similar to the contrast sensitivity function that we had back when we studied vision. Here what we're getting is a plot of the sound intensity that is needed to detect a sound, the softest sound that we can detect at various frequencies, and you and I might be maximally sensitive at something like 1,000, 2,000, or 3,000 hertz. We can hear much higher frequencies as well, but we're going to need more acoustic energy in order to do so. We might be able to hear very low frequencies, maybe on the order of 30 hertz or 20 hertz, but we're going to need a considerably larger amount of acoustic energy in order to hear those, so we can get these audibility functions. If the child who has a language-based learning impairment goes to the school nurse or the audiologist and is measured during this typical routine where we have them raise their right hand or left hand to indicate where the sound is coming from, they're going to do just fine on that. Their problem is not with respect to their general audibility function. We sometimes call this an audiogram. That's not their problem. The problem is one in timing. They need wider intervals of time in order to make a discrimination. And that's typically not caught during these kinds of tests. So a lot of kids go undiagnosed, unfortunately. Okay, let's go back over to our PowerPoint presentation. Okay. So the auditory systems of children with LLI have lower than normal or more coarse temporal resolution. They probably can't make discriminations in 5 or 10 milliseconds. They might need, for example, 20 or 30 milliseconds. In LLI, events that are physically distinct and discriminable to most children become blended together in time. So there's, again, a failure of discrimination, and this now makes the child unable to understand as precisely as other kids what the teacher is saying. Okay, so that concludes our introduction to speech perception. I hope, as always, you'll make a note of what was particularly clear in this session and also what was less clear, and bring those comments to class. See you in class.